So when we're talking about binomial distributions, obviously the first thing we want to do when we're looking at any distribution is define our random variable. And then we go and figure out whether or not it truly is binomial by checking the bins. One of the things we always want to get in the habit of doing is finding out whether or not we can use a normal approximation. The normal approximation for binomial distributions allows us to use the normal curve, the z-tables. There's a lot of things that it buys us. As the number of observations n gets larger in a binomial distribution, the binomial distribution gets close to being a normal distribution. So as n increases, our binomial formulas become less accurate and our normal approximations become more accurate. So you want to always check to see if n is large enough to use the normal approximation. So what does it mean to be large enough? We have a rule of thumb. I like to call this the test for normal approximation rather than just rule of thumb, because you'll find in the next few days we're going to end up with many rules of thumb. And so rather than just calling everybody the same thing, I kind of want to talk about what specifically they are. So this is a test for normal approximation. We'll use the normal approximation to the binomial distribution when n and p satisfy two conditions. N times p, that was the mean, but notice it's also the number of successes that I'm going to have. That's the number of observations times the probability of success. That would tell me the number of successes. So I need the number of successes greater than or equal to 10, and I need the number of failures, or n times the probability of failure, which is 1 minus p, to be greater than or equal to 10. So the number of successes and the number of failures both have to be greater than or equal to 10. So before you compute any probabilities using binomial CDF or binomial PDF, you want to check to see if these conditions are satisfied. If they are, we're going to use the normal approximation. If not, we'll use the binomial formula or the calculator. Always make sure that you check for the normal approximation capability. So if we're going to use a normal approximation, then we want to be able to understand what's the mean and the standard deviation, so that when we talk about a normal distribution, we always give it this is our standard notation, that we would have the mean and the standard deviation. So if x has a binomial distribution with n trials and a probability of success p, when n is large enough, np greater than or equal to 10, n times 1 minus p greater than or equal to 10, then the distribution of x is considered to be approximately normal, with the mean, np, well, that's just the mean of a binomial distribution, and the standard deviation, the square root of np, 1 minus p, that's just the standard deviation of a binomial distribution. So I can show it this way. I have the normal distribution, normally distributed, with mean np, standard deviation, square root of n times p times 1 minus p. The accuracy of the normal distribution improves as the sample size increases, and it's most accurate when p is close to 0.5. So p being close to 0.5 says my probability of success is close to 50%. That's going to be as close as I can get to being a nice symmetric type distribution. And so if I think about that 0.5 being that most of my answers or most of my random polls are going to end up being close to the 50%, then it's going to end up taking fewer samples in order to be able to get it to look normal. So symmetric, bell-shaped, single, pumped, in order to be able to do it. It is least accurate when p is close to 0 or 1, and it takes a lot more samples when I have a probability close to 0 or a probability close to 1, probability of success. It takes a lot more samples to get it so that I can use the normal approximation. So let's take a look at an example here. This is going to take us a little bit to walk through, so just be patient with me. A recent survey asked a nationwide random sample of 2,500 adults if they agreed or disagreed with the statement, "Shopping is often frustrating and time-consuming." Suppose that 60% of all adults would agree with the statement if asked. What's the probability that 1,520 or more of the sample agree? So there's the problem I'm trying to work with. Let's work through it step by step. The first thing that I want to do is I want to define my random variable. So x is going to equal, this is my random variable x, the randomly chosen person, the number of people who agree with the statement. So in my sample, how many of them actually agreed with the statement? That will be x. The second thing I want to do is I want to check the bins. I need to find out, is this a binomial situation, a binomial distribution? So when I check the bins, I go through and I say, binary, is it binary? Am I dealing with success or failure? And my answer is yes. Success being that they agree with the statement, failure being that they don't agree with the statement. Independent, again, yes, we're going to assume the opinions of people are independent. So as I choose one person and ask them how they feel, it would be independent of the next person that I chose. Is the number of trials fixed? The answer is yes, 2,500. I have a random sample of 2,500 adults, so I only have 2,500 chances to either succeed or to fail. And the next question I'm asking is the same, do I have the same probability of success for each person I poll? And the answer is yes, because I have 60% of all adults agree with the statement. So my probability of agreeing of success is 0.6. So I've checked the bins, and I do have a binomial distribution. So that was step number 2. Step number 1, defining my random variable. Step number 2, checking the bins. Now that I know I have a binomial distribution, and notice that I can show this in my format, but binomial distribution with n of 2,500 and p of 0.6, my next question is, can I use the normal approximation? I have to go and check the numbers in order to find out if that's true. So I check to see if n times p is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10. If I plug in the numbers, n is 2,500, p is 0.6. It happens to equal 1,500, which is well over 10. So we're good to go. Then we also look at the number of failures, 2,500, n times 1 minus p, the probability of failure, which is 0.4. That equals 1,000. And again, we're good to go. It's greater than 10. Therefore, I can use the normal approximation. If I'm going to use the normal approximation, then I need to come up with a mean and a standard deviation. So yes, a normal approximation can be used. So I calculate out my mean, mu equals np, this is mu sub x, equals np, which is 2,500 times 0.6, or 1,500, the number of successes. I also have to calculate out a standard deviation, the square root of np, 1 minus p, which is the square root of 1,500 times 0.4, or 24.49. So I'm going to use the normal approximation, where I have normally distributed x with a mean of 1,500 and a standard deviation of 24.49. Now we can answer our problem. So the problem asked me, what's the probability that more than, greater than, or equal to 1,520 we're going to answer that they agree? Now notice, greater than or equal to, as soon as I moved into normal approximation, I'm dealing with a continuous random variable. No longer am I dealing with binomial distribution and a discrete random variable. So be very careful about that. Because it is continuous, then it means that the equals can either stay or go, because in a continuous random variable, the probability that x equals a number will always be 0. I'll convert this over to a standardized score, which means z, I'm going to change in this 1520 into x minus mu, 1,500, over sigma, 24.49. Or I'm looking for the probability that x is greater than 0.82. I draw a picture. You'll notice that if I put it on the z-curve, then 0 is my mean, 0.82, and shaded above is what I'm looking for. If I left it on my x-curve, then 1,500 is my mean, and 1,520 is what I'm looking for, greater than. I can put this in my calculator, or I can use my table, either one, and I come up with the value 0.2061. That means that there is a probability of 0.2061 that 1,520 people or more will agree with the statement, shopping is often frustrating and time-consuming. Now, if I went back and did this with a binomial calculation, which I wouldn't do because, again, I've already proven that I can use my normal approximation. If I looked at it from a binomial standpoint, I would say the probability that x is greater than or equal to 1,520. Now we're back in binomial land. That means it's discrete. That's going to equal 1 minus the probability that x is less than or equal to 1519, not 1520, but 1519. I have to do it this way because binomial CDF on my calculator will only handle less than or equal to. So I do 1 minus binomial CDF of NPK, 2500, 0.6, 1519, and I come up with 0.2131, which you'll see is very close to it, but it's not exactly the same. In your notes right now, it actually talks about how to graph binomial distributions on the calculator. It gives you step-by-step instructions. So I would like for you to try it, and we will try it again in class tomorrow, and I'll be able to, or Monday, and I'll be able to answer any questions that you have on it at that time. Good luck with it, and I'll see you Monday.